So welcome everybody to today's seminar. So we are very happy to have Tomáš Brauner from Stavanger, who will tell us about something that he has been working on and is very well known for developing effective field theory for broken symmetries, especially when space-time symmetries are broken. And he has extended this also. He has pointed out many applications in quantum matter physics with his collaborators. And I just learned from him that I missed him in Vienna by a few months. So it's good to meet him finally, although it's online.
Same here, yes.
Okay, so let's hear from him then now.
Thank you. Okay. First of all, thanks a lot, Ayan, for the invitation. It's great to meet new people just virtually like this, but well, this is actually an opportunity to give a talk for you at your institute and at other people who might want to join this talk. So as the title suggests here, I'll try to give a kind of introduction and background on effective field theories for spontaneously broken symmetries, which is a topic that I have actually been working on ever since I was a PhD student. But so it's a kind of overview. So I will talk about stuff I have done roughly in the last decade, but I will also get to some recent work of mine in the second half of my talk. I was asked to give a colloquium style talk, and so I will start with a very broad introduction on undergraduate level for students who might be in the audience, and I kindly ask experts to be a little patient. I get to somewhat high level later on, but let's get started. So that's it. I was teaching for a number of years an undergraduate course on thermodynamics and fluid dynamics. And that's a great example to introduce the concept of effective field theory, because what I would do in that course would start by introducing the kinetic theory of ideal gases, and from that motivate the macroscopic quantities, which is the temperature and pressure. And so this illustrates one of two main features of what effective field theory does. That first, you can simplify the description of a physical system tremendously. So you don't have to bother about all the kinematics of all the huge number of particles that you have in the gas. So you just get away with a few parameters. So in that sense, it's really effective. On the other hand, this also shows this example how one can really change the description dramatically, because the descriptors you use are very different on the microscopic level and on the macroscopic level. Now, if you might complain that this is not field theory, because if you have a homogeneous system without any external fields and the temperature and pressure really are constant throughout, it becomes a field theory if you kick the system slightly and perturb it and you look how it responds, because then what this becomes basically is hydrodynamics. And so this underlies another two features that are very common for effective field theories. First of all, the physics, the low energy physics of systems with some order is dominated by collective behavior of the fundamental constituents, not by the motion of the individual particles inside that we don't resolve. And second, the description is largely constrained and dominated by conservation laws. Now, what this all has to do with spontaneous symmetry breaking, that's not immediately obvious. And that's because when we learn about spontaneous symmetry breaking in quantum field theory classes, usually we talk about breaking of internal symmetries. And what matters in this case of hydrodynamics, of course, is the space-time symmetries, is the energy momentum conservation. But so let me show you one more example of the internal symmetry side, which is in many respects much easier than dealing with space-time symmetries. This is another very well-known example of a ferromagnet, where below the Curie temperature, spins in a ferromagnetic system align spontaneously, and you get what we call an order parameter. And the ordering breaks some symmetries that otherwise the microscopic dynamic would have. So here is for the undergraduate student now, what happens when you perturb the system slightly and you ask about the low energy physics of a ferromagnet? Well, if you say push a ferromagnet locally, and you may deviate the direction of a few spins, due to the mutual interactions, the perturbation will propagate. It will propagate in the form of spin waves. So those are the degrees of freedom of the low energy effective theory, in terms of which one describes physics of ferromagnets at low energies. For the future reference, I'll also introduce a different picture. So what I showed you here is a kind of snapshot of a spin wave in real space. But I also introduce a kind of dual picture where one can represent the same thing in field space. If you think of the local magnetization as a vector with fixed length, where you just look at the direction, then you're basically thinking of a degree of freedom that lives on a sphere. Okay? It's only the direction that matters. And you can think of the spin wave as a kind of fluctuation of a field that lives on a sphere around some expectation value. So the collective degrees of freedom that characterize the dynamics of systems with some order, one can think of as fluctuations of the order parameter. Now I'll use this. This is very common thinking in condensed matter physics, not a bit less common in high energy physics, but I'll use this frequently later. Now, if one last slide on the undergraduate introduction. So how come that, as I claimed, the physics is dominated or governed by symmetries? And this is something that one can understand without field theory, just with the basic knowledge of classical mechanics and thermodynamics. Because what we do when you have some system with some order parameter in thermodynamics, we develop a Ginzburg-Landau theory description of the order parameter. And for that, we write down some free energy functional. And this is how it might look. Okay? So you have this order parameter, which is our unit vector that defines the direction of the local magnetization. And you write down this kind of gradient term into basically Hamiltonian. And there is a single constant, a single coupling of that Hamiltonian, this rho here, which is called the spin stiffness. And this single parameter defines the dynamics of the spins, of spin waves. Now, the Hamiltonian itself is not enough, unlike a Lagrangian, because we need to know the canonical structure. So we need to supply some additional information. And that additional information comes through this here. So this is, it's all classical. So this is a Poisson bracket. And it's a Poisson bracket of you can think of it as local spin density. And it just says that when you have lots of spins in your system, then spins at different places are independent degrees of freedom, whereas the different components of the spin operator at one place satisfy the usual angular momentum algebra. So you have this kind of Poisson bracket, which defines the canonical structure. Together with the Hamiltonian, this defines completely the dynamics of spin waves. So you can derive the equation of state for the spin waves just by combining these two pieces of information, and you get this so-called Landau-Lifshitz equation. I'll skip the details, but as I said, this is an exercise that an undergraduate student would be able to complete. From here, you can see one characteristic feature of spin waves in ferromagnets, that is the energy, which comes from taking the derivative here, is proportional to the momentum squared, which comes from the two spatial derivatives hidden in the Laplacian on the right-hand side here. And this is typical for something that's called type B GOLDSTONE bosons that I'll mention later on. But I just wanted to show this here to illustrate how the physics is pretty much completely fixed by symmetry. The only thing that's not fixed by symmetry is the value of this one coupling here, rho, the spin stiffness. Everything else is. Symmetry dictates this commutation relation. That's just angular momentum algebra. And to some extent, symmetry is also hidden in the form of the Hamiltonian here, because the fact that the Hamiltonian only includes gradients says that if I take the spins and I rotate them everywhere by the same angle, it doesn't cost any energy. I don't create any gradients. And this is typical for systems with broken symmetry, where you have degenerate ground states. If you start with one orientation of spins everywhere and you rotate it by the same angle, it doesn't cost any energy. So the symmetry of the system is also implicitly hidden in the form of the Hamiltonian here. So that was my mild introduction, and now let's get into how we actually construct effective field theory for systems with broken symmetry. The first thing that we have to sort out is, well, we want to construct some effective theory for some system where symmetry is spontaneously broken. Well, what are the corresponding degrees of freedom? So that's equivalent to understanding what kind of low energy excitations there are. And when we have spontaneously broken symmetry, that's what we called GOLDSTONE or NAMBU-GOLDSTONE bosons, which are implied by the GOLDSTONE theorem. Well, the standard textbook knowledge that we learn about in quantum field theory classes is that there is a one-to-one mapping, one-to-one correspondence between broken symmetries and GOLDSTONE bosons. But this is not always true. In general, the number of GOLDSTONE bosons will be smaller than the number of broken symmetries. And as far as I know, there are two general mechanisms how this can happen. One comes at the stage where we want to set up a correspondence between broken symmetries and between the fluctuations of the order parameter, which I claimed previously. Well, it's the fluctuations of the order parameter that describe waves in ordered systems and that correspond to the Goldstone bosons eventually. Because it turns out that you can have different symmetries which are spontaneously broken and which will lead to the same fluctuations of the order parameter. So there is some kind of duplicity, some kind of redundancy, which is typical for space-time symmetries, but also for some internal symmetries that I'll mention later on. So I'll get back to this. I will not explain in more detail here. But then once you have identified independent order parameter fluctuations, there's still an additional step whereby the number of actual states you observe in the spectrum can be lower than that. And that's possible in case you have two different fields that can be canonically conjugated. And so this was apparently first observed by NAMBU only in the early 2000s. So generally, otherwise people knew concrete examples, of course, long before that. And it gave rise to modern classification of Goldstone bosons that nowadays we call type A and type B, where type A Goldstone bosons are in one-to-one correspondence to broken generators, whereas type B are in correspondence to pairs of broken generators, constrained by the condition that you take two charges, you take a commutator, and that should have a non-zero expectation value. And the simplest example of that is in the ferromagnets, where you have spontaneous alignment of spin, so you have non-zero expectation value of one component of spin. That's proportional to the commutator of the two other components. So that's what we see there. And so you have two broken symmetries, but only one type of spin wave. So once, yes.
So the type Bs are only possible if the vacuum doesn't break Lorentz symmetry?
If it does break Lorentz symmetry.
Or if it does break
yes.
Lorentz symmetry, right?
Yes. Because it requires, as I'll show later when I actually work out the effective Lagrangian, it requires a term in the effective Lagrangian that contains one-time derivative.
Sure. Okay. Yeah.
So you need to break Lorentz symmetry either explicitly or spontaneously. Yeah. Thanks. Thanks for the question. Yes, that's a good point. So we have the degrees of freedom now. Now we have to set the stage, and that is we want to set up a field theory for those degrees of freedom for the Goldstone bosons. And well, I already mentioned previously in my example with the ferromagnet that the low energy degrees of freedom, the spin waves basically live on a sphere, and this generalizes very straightforwardly to a system with arbitrary symmetry. I'll call it G, that's usual notation, that's broken to some subgroup H. And all the vacuum states, which are all degenerate with respect to each other, they span the Coset space, G over H. And so we can think of the Goldstone bosons as fields that take value on the Coset space. So at the end of the day, mathematically or geometrically, the effective field theory for a broken symmetry is an effective field theory for fields that take values on the Coset space of the broken symmetry, which is the vacuum manifold, mathematically speaking. So now we have the degrees of freedom, and we know what roughly what the corresponding fields would look like. So we can start constructing the effective theory. I'll take a rather pedantic route here. I'm sorry for those of you who might want to take a shortcut to the final answer, how the effective field theory looks like. So I want to advocate here a bit of a sort of historical approach, which was advocated by Leutwiler in the mid-90s. So rather than trying to build an effective theory for spin waves or some other collective modes bottom up starting from the symmetry, think of having some microscopic theory. Like think of QCD, which is a theory of quarks and gluons. And at low energies, QCD reduces to pseudoscalar mesons, pions and kaons, which are the pseudo-Goldstone bosons of broken chiral symmetry. So we have some microscopic description, and we have some low energy effective theory, where typically they would be described they would be phrased in completely different degrees of freedom. So it seems difficult at first sight to match the two. How do we connect the microscopic theory to the effective theory? Well, one way to do so is to use the generating functional formalism, and we couple both theories to some background field, to some source. which when you then integrate over the dynamical fields gives rise to a generating functional. And the point now is that if you couple both the microscopic and the effective theory to the same source, then you get generating functionals which you can compare, and they should match at least in the range of validity of the effective theory. Now you might ask if it's actually possible, since I have completely different degrees of freedom in the microscopic and effective theory, is it actually possible to couple, to find sources that I would be able to couple the both? And here's where the symmetry comes, because symmetry guarantees the existence of conserved currents. Again, in terms of quarks and gluons and in terms of pions, the conserved currents of the global symmetry of QCD will take a completely different form, but they are guaranteed to exist. Once I have them, I can couple them to background gauge fields, because currents couple to gauge fields. And in this way, I can write down a generating functional in terms of background gauge fields that are coupled to all conserved currents of my theory. The word identities, which are implied by the symmetry, then guarantee that the generating function will be invariant under background gauge transformations of the background gauge fields. So now I can play the same game also for the effective theory. I know what the generating functional should be now. It should be gauge invariant, at least in absence of anomalies. And on the effective field theory level, I should be able to reproduce the generating function from some effective action. Now it is usually a starting point that we have an effective action for pions. It should have the symmetry of QCD. But this is somehow is not guaranteed a priori, because we don't know what pions are as fields a priori. The only thing that we know is the generating functional. So this is a set advocating a sort of pedantic approach due to Leutwiler, who actually proved mathematically that one can define GOLDSTONE fields in such a way that a gauge invariant generating functional will be reproduced by an effective action that itself is invariant. So that's not an assumption, that is a result of Leutwiler from 1994. That one can find a parameterization of GOLDSTONE fields such that the effective action, which is now a functional of both the GOLDSTONE fields and the background fields, is invariant under the joint gauge transformation. That's something that one usually takes as a starting point. So now one can continue and say, well, okay, so now I need to know how my GOLDSTONE fields actually transform. And this is, for the expert, this is something that's called the coset construction, and it's very old stuff. It goes back to the work of Callan, Coleman, West, and Sumino from 1969. So it's more than half century now. I don't need to go to details. The only thing that matters is that we can think of the GOLDSTONE fields as being contained in some matrix field. I call it U because usually it's unitary, at least for compact Lie groups. And we can think of the action of the symmetry group on it just by multiplying this by a group element from the left, so by left multiplication. And because we now are talking about local symmetries, local symmetry transformations, it appears that I can choose a symmetry transformation which just eliminates the GOLDSTONE field altogether. I can just choose a group element that is just the inverse of this. We can think of this as a kind of unitary gauge. And what it does is that if you have the action originally that was functional of the GOLDSTONE fields and the background field, now the GOLDSTONE fields disappear and the background field gets sort of dressed. It just says that the GOLDSTONE and the background fields don't appear independently in the action, but they appear only in such a particular combination. This is, by the way, for those who are familiar with the coset construction, basically what you get here would be called it would be the gauged version of the Moore-Cartan form of the broken symmetry. So now you have those dressed gauge fields, and the usual thing to do is that, well, these take values in the Lie algebra of the symmetry, so you can decompose them into broken and unbroken components. The notation may be a bit unusual here, but otherwise the rest is quite standard. The broken component behaves roughly as covariant derivatives of the GOLDSTONE fields. It transforms covariantly, and it's a good building block for constructing invariant Lagrangians, whereas the unbroken component behaves as a gauge connection of the unbroken subgroup. So now we take these and put them together and start constructing Lagrangians. And here's another contribution of Leutwiler. So it's a kind of theorem that you can always write the effective Lagrangian in terms of these dressed fields, and you can split it up into two pieces, where one piece is strictly invariant under the symmetry. And that's the usual stuff. You know, you take fields, you take their covariant derivatives of that. By that, you construct tensors with many indices, and those you just put together, multiply them, and contract indices in a way that respects the symmetry. This is something that we have known for many, many years, as said, more than half century. Then there may be some interesting contributions to the Lagrangian which are not invariant themselves, which are only invariant up to a surface term. And Leutwiler showed that those can be, without loss of generality, assumed to only depend on the gauge connection, but the dressed one. So, but if you forget that it's a dressed gauge field, we can think of this as an action for the gauge field of the unbroken symmetry. It's an action for gauge field. And this is something that we call the Chern-Simons. These kind of Lagrangians, funny Lagrangians, which are only invariant up to a surface term, they map on Chern-Simons theories for gauge fields of the unbroken symmetry. And they lead to interesting topological effects, as I'll mention shortly. So now we have basically a general methodology how we can construct an effective theory, at least for internal symmetries. And then I can just flash some results here. If we now go back temporally to relativistic theories, the answer is very simple. At least at the leading order in derivatives, where we have only two derivatives in Lagrange, and this is the general answer. So you have a covariant derivative of Goldstone field, another one, you contract the Lorentz indices, and then you contract the internal indices A and B sitting on the Goldstone fields by something which is a non-trivial function of the Goldstone fields, and it turns out to have the geometric interpretation of an invariant metric on the coset space. So this is something that people have actually known for many years. The new thing, the relatively new thing, actually, which was not even discovered by Leutwiler, but came in the last 10 years, is that now we actually know explicitly how to calculate this. And here's the answer, where now omega, again, is something that people call a Markov form. And the C here, that's some numerical matrix of low energy coupling. So that's a constant symmetric matrix, which is constrained to be an invariant tensor of the unbroken subgroup, technically speaking. The covariant derivative of the Goldstone fields is built up in the usual way. So you have a derivative, then you have a linear coupling to the background gauge fields, and finally you have a bit that defines how the Goldstone fields transform under the symmetry transformation. And that's something that in geometric terms would define Killing vectors of the symmetry group on the coset space. Now, we don't know how all these functions that depend on the Goldstone fields would be we don't know any closed form for them in general, but at least if you're only interested in perturbative physics, you can calculate them order by order in a power expansion in Goldstone fields, and it's just a sample. Right? This can be done completely generally, where F are the structure constants. This is just sample results that are valid up to second order in the Goldstone fields. So that's a general answer for relativistic theories. Now, if you go non-relativistic, things become slightly more interesting. First of all, the term that I had here, now we can split up temporal and spatial indices. So we have actually two different terms in Lagrangian, both containing two covariant derivatives, and in principle independent metrics. Here, this GAB, and it's called GAB bar. And then the new thing is that now you can have terms with a single temporal index, which can be either a term with the time derivative of the Goldstone field, or a term which is linear in the temporal component of the gauge field. I don't even write down what these coefficient functions are, but they can be calculated explicitly. And this is something that actually Haruki Watanabe has found back in 2013. He found for the first time explicit solutions, explicit expressions for these functions. What Leutwiler did back in the 90s was that he derived some differential equations for these functions using their geometric formulation. So instead of showing you more and more general results, let's see what all this actually implies physically. So first thing, since I already mentioned perturbative physics, we may expand the Lagrangian to second order in fields, because that will give us some information about the spectrum. And this is what you get. Now, this interesting part of Lagrangian, which only has one temporal index, contains a term that's linear in the gauge field, and that simply says that this effective coupling E has the interpretation of the density of the conserved charge in the ground state. You just have to remember that we can generate net occurrence by taking variation of action with respect to the gauge field. And so if you have something linear in the gauge field, and its coefficient is just is the expectation value of the conservative charge. And in the term that contains a time derivative of the Goldstone field that's bilinear and one time derivative, we have the same coupling, but now multiplied by the structure constant of the symmetry. And that just means that this term, this coupling here, is the interpretation of the expectation value, but now of a commutator. And if you remember, when I mentioned the type A and type B Goldstone bosons, I said that a type B Goldstone boson corresponds to a pair of charges whose commutator has a non-zero expectation value. Here you can see that. So this shows that the type B Goldstone bosons require a term with a single time derivative, and this shows where it comes from, such a term. And yes.
Can I ask? So this CAB bar and CAB, there should be equal in relativistic theory.
Yes.
Now the expectation value of this QA comma QB, how does it affect? What I want to ask is, how exactly what is the necessary condition the CAB bar will be different from CAB, and how do you actually compute these two things in when you do not have relativistic symmetries? I mean,
how you compute them? Well, from the point of view of effective field theory, they are low energy coupling, so you can't determine them. You would need some microscopic model, right, to do the matching of the effective field theory parameters. But from what the effective field theory does is that it fixes the forms of the operators in the Lagrangian, but not the values of the couplings. So those are undetermined. In principle, of course, you can calculate them if you have some microscopic model. Now, but they are independent. See, CAB and CAB bar are independent of this first term here. So even if this first term is absent, the CAB and CAB bar can still be different. An example would be antiferromagnets, where this term with one temporal index is missing. And so the effective Lagrangian for antiferromagnets really at the leading order would only contain these two terms. And the CAB and CAB bar will be different, simply because the spin waves in ferromagnets don't propagate the speed of light. So you can think of that of the effective theory having some kind of pseudo Lorentz invariance with the different phase velocity. But if you try to add higher order corrections, of course, you would lose even that.
Yeah, actually, what maybe I got lost was that in the previous slide, you were talking of this two metrics, GAB and right
here.
You said that one can compute okay, the two derivative term is kind of fixed. The pi dependence is fixed by the construction of the theory. So actually, my question was here that how to. Yeah, that's what I wanted.
So they are, yeah, okay. I was going through all the details, of course, a little quickly, but here is how you can compute the metric. So omega here, that's the Morikawa form that's fixed by symmetry. Here, this is fixed. This dependent on pi is fixed by symmetry. What is not fixed by symmetry is this C here. That's just the matrix of coefficients. So for the two metrics I call G and G bar, the expression would be the same, except that then here the coefficients would be C and C bar. So that would be parameterized by different sets, different matrix coefficients, different matrix couplings.
I see, and this is something that will depend on whatever the microscopic theory is.
Yes, exactly. But the dependence on the Goldstone bosons is completely fixed by symmetry of all the operators.
Okay, thanks.
Yeah, thanks. Okay, so that once you've established here that you can have a lower number of Goldstone bosons and broken symmetries, because some of the fields here, one can see it here clearly, are canonically conjugated. Okay? The term which is bilinear in two fields, and one of them carries time derivative. It means that pi b is the canonical momentum of pi a, roughly speaking. So they are canonically conjugated, and they couple to the same physical state in the spectrum. And that leads to a modified counting of a number of Goldstone bosons. And here is the final answer. What you need to know is first the dimension of the coset space, and you need to know the rank of this object here. If you think of it as a matrix, where A and B are run over all broken generators. So you need to know the rank of that. Once you know that, that's the additional low energy data that you need to fix the number of Goldstone bosons. So this is still rather old stuff now, by now almost 10 years. Let's have a bit closer look at those Chern-Simons like Lagrangians, because there's lots of interesting stuff hidden in them, and I already advertised that there are some topological aspects which once I say Chern-Simons, you might expect, because Chern-Simons theory has non-trivial topological properties. If you now play the game of just constraining the effective action by invariance under small gauge transformations, so no non-trivial topology, no large gauge transformations, what you find up to fourth order in derivatives, you have only two possibilities. The one I already showed you, that's linear in that dressed gauge field, and one that looks just like the usual Chern-Simons theory, which is cubic in a gauge field. I was just trying to be extremely general here. And so in writing these expressions, I didn't assume anything about space-time symmetries, except that translations are unbroken, space-time translations, but the rotations can be anything. They can be even missing. You don't have to you can have some crystal lattice with just a discrete rotation symmetry. It doesn't matter. The only thing that will affect is that then these effective couplings now have are some rather complicated tensor couplings which contain internal indices and which contain also space-time indices. So this, in terms of gauge fields, you have interesting contributions to the Lagrangian which look like Chern-Simons theory. On the other hand, you might think, well, let's switch off the external sources, because the gauge fields I'm talking about here, after all, are just external fields, and let's just keep the GOLDSTONE bosons. Then if there is some non-trivial topology in here, then it should somehow reflect the topology or the geometry of the Gosset space on which the GOLDSTONE bosons live. And the answer is yes. And actually the answer to this has been known since the mid-90s even. And it turns out that these Lagrangian, which is responsible for type B GOLDSTONE bosons, is classified by second theorem cohomology of the Gosset space. So you have some non-trivial two form on the Gosset space whose one form potential defines this Lagrangian. And that those are classified by U1 factors of the unbroken subgroup. So the ferromagnet is the simplest example where SU2 spin symmetry is broken down to U1. This more complicated cubic Chern-Simons term is classified by the fourth theorem cohomology of the Gosset space, where you have some non-trivial four form whose three form potential then defines this Lagrangian. But more than some technicalities, physics may be more interesting. So let's first stick to the term with the single time derivative, because there's lots of interesting stuff hidden in there. Apart from changing the dispersion relations of GOLDSTONE bosons, changing the number of GOLDSTONE bosons, it does more. It gives rise to a Berry phase. So think of now, again, switching on a background field. What we are used to, if you have some external perturbation, such as a background field, it breaks symmetry explicitly, and it tends to align the ground state in a certain specific direction. In my ferromagnet analogy, you think of switching on a background magnetic field. It will align all the spins in the direction of that magnetic field. So now suppose that you take that background field and you start to change it adiabatically. And by doing so, you are driving the ground state of your system through the Gosset space. And you can go for a little round trip. You can take the ground state of your Gosset, of your system around a closed loop in the Gosset space just by tuning the background field. And it turns out that upon going around the closed loop, the ground state picks a phase, which is just a Berry phase. And the Berry phase is governed by exactly the same term in the effective action. Even more curiously, there is a funny feature that's associated with the same term in the action that in quantum matter physics is sometimes called a linear momentum problem. In case it sounds a bit esoteric, what it means is actually very simple. You have a term in the effective Lagrangian that's linear in time derivative. So now if you calculate the canonical energy and momentum using Noether theorem, it's linear in time derivative. So when you do the Legendre transform, this thing will drop. It doesn't contribute to the Hamiltonian. Okay, momentum, that's more interesting. This then does contribute to canonical momentum. And as it turns out, what you get, the contribution to canonical momentum, is just looks exactly the same, except that you have to replace the dot with the spatial derivative that carries an index, which labels the different components of momentum. That's how the corresponding canonical momentum will look. And that's strange, because now this thing is not invariant under the symmetry. It shifts by a surface term. And that means that the contribution to the canonical momentum that you get out of it will also not be invariant under symmetry. And it's something weird, right? So in ferromagnets, where you have internal SU2 symmetry and then you have some space-time symmetry, the canonical momentum of spin wave, the canonical momentum density of spin wave, is not invariant under the internal SU2 symmetry. And the same for any other system which features this kind of topological term in the action. The integral momentum is fine. We integrate the whole space, the surface term disappears, and you're happy. But it still feels sort of strange that one should not be able to define momentum density locally, because you might think of a microscopic description, which is a description in terms of particles, and it would sound strange that you cannot define momentum of individual particles in the microscopic description. So in concrete physical examples, physical system where this happens, and one is, for instance, ferromagnets, another is the so-called A phase of superfluid helium-3, the resolution is that one tends to find other gapless degrees of freedom which just compensate for this problem. And in those cases I mentioned, they are fermions. They are not Goldstone bosons. But as far as I know, this problem actually doesn't have a general resolution yet. That would be phrased in terms of the geometry recursive space and in terms of field theory. Yes. One thing that's also interesting is that this term with a single time derivative can be cast as a Wassermann-Witten term. So for people who like anomalies, if you take that second cohomology generator that I mentioned previously, which defines this term, and you can integrate it over some two-dimensional manifold, and that will give you the action for the spin waves. Now, what is that two-dimensional manifold? What you have to do is that you take time manifold as a one-dimensional and you compactify it to a circle, and then extrapolate the circle to a two-dimensional disk. So this is the construction that one usually does for Wassermann-Witten terms, that you add one more space-time dimension, you extend the definition of your fields to one extra dimension, and the price for that is that you can now formulate the action in a manifestly invariant manner at the cost of having to add one extra dimension. So this is what you can do here also. And okay, this is just an example for ferromagnets where that two form I was talking about is just the volume form on the two sphere. Here the Cossette space is two-dimensional. It has a natural two form, actually the single non-trivial cohomology generator, which is the volume form on the two sphere, which is this in terms of our unit vector field n. And then now we integrate it over the two-dimensional disk I mentioned. And in this way, you get a manifestly invariant description of the action of ferromagnets. You can also get the corresponding Lagrangian for the spin waves, but it looks like this. So you get now really Lagrangian in terms of the physical space-time coordinates, no extra dimensions, but the price is that you lose the manifest rotation invariance. But you have this one-time derivative here, which guarantees that you get the quadratic dispersion relation for the spin and so on. For the cubic Chern-Simons term, things are slightly more complicated. They don't affect the spectrum of the Goldstone bosons. What they do affect are interactions. And it turns out that this is something that people apparently had not noticed before, that if you take that cubic Chern-Simons term, it gives rise to an interaction of 4 Goldstone bosons with 3 derivatives at the leading order. This is somewhat similar to what people observe in hadron physics, where the Wassermann-Witten term of QCD gives rise to interactions, but of 5 mesons with 4 derivatives, and that's known to be responsible, for instance, for a scattering process where 2 kaons scatter and they produce 3 pions. This is something that's superficially similar, except that first of all, it doesn't require any anomalies. And second, there is one less Goldstone boson and one less derivative in the corresponding Lagrangian. I don't know of any physical realization of this, and I also don't know of anybody having actually discussed this kind of topological interaction previously. So it's in principle something that might be worth looking into still. Yes, I will skip probably this, and I will just mention here before I move to the next and last part of my talk, a bit of a history. Once we talk about topological terms, and especially that I mentioned the words West and Sumino, it's mandatory to at least mention briefly anomalies, because everything I've told you until now was based on the assumption that there are no anomalies. Then the generating function is exactly invariant, and you get constraints of the effective action and so on, classified Lagrangians and so on and so forth. Once you admit anomalies, the generating functional of the theory is no longer invariant, but it shifts in a well-defined manner. And so you still get exact word identities, except that they are anomalous, and you get constraints on the effective theory as well. And of course, this is a very old problem because the chiral anomaly appears in QCD when you couple it to external fields. And so, of course, the construction of Wassermann-Witten terms for the low energy effective theory of QCD is a very old problem that was addressed already in mid-80s, I'm sorry. And Witten was the first who came with the picture of having manifestly invariant action at the cost of adding one extra dimension, which also highlights the topological properties of the Wassermann terms. Interestingly enough, people haven't had really a general description of the Wassermann terms for general Coset space. There are some differential geometric works out there on the market, for which you have to climb over a rather high barrier if you want to understand the notation and all the technology. And so they are not so extremely useful for practitioners who are interested in particle phenomenology, and they need to know the Wassermann-Witten term for a certain specific Coset space or broken symmetry. So back in the mid-80s, what people did basically just worked out how these Wassermann terms look for the chiral Coset spaces where you have the same symmetry or two isomorphic symmetry groups acting on the left and on right-handed fermions, being spontaneously broken down to the diagonal subgroup. There are other theories, QCD-like theories, which have different choice of gauge group or different choice of representations of quarks, where the global symmetry is different. And it may look like this, for instance. This is what you get when if you take a QCD-like theory where you change gauge group or change the representation of the quark so that the representation is pseudo-real. For n flavors of quarks, you get this global symmetry breaking. Surprisingly enough, as far as I know, the Wassermann terms for that were only worked out in the early 2000s. And then there are other examples, for instance, this kind of Coset space, which were constructed even later. So I just want to show here to advertise a bit my recent work with my postdoc Helena Koleshova, where only 2 years ago we actually managed to work out the Wassermann terms for a completely general Coset space. We're not aware of this having been done before, although, as said, implicitly this is contained in rather technical mathematical works, but ready-made expressions for Wassermann terms for a general Coset space didn't appear before, as far as I know.
So Thomas,
so
can I ask something?
Yes.
Something basic. It's about this slide and also the one slide before. So this Wassermann-Witten terms, do they correspond to something in the microscopic theory that I can compute and match?
Well, yes. So they come from the anomaly. So in principle, if you integrate out fermions, and they can be just free fermions, you don't need to resolve QCD dynamics. You can just take free quarks and couple them to a set of background gauge fields, and you integrate them out. You calculate the determinant of the Dirac operator with the background gauge fields in there. And from this, you can get the Wassermann term explicitly. You can calculate it. Yeah, it's possible.
Okay, thanks. Okay,
yeah. One other. So what most of these original works did was they just constructed the Wassermann terms by restricting them by symmetry, and then then depending on the exact geometry of the Coset space, you may find that there is a unique Wassermann term up to overall normalization, and then you just end up with a single coefficient that you have to calculate it to match, and that you can also match by calculating the anomaly. You can calculate a single triangle diagram in the microscopy theory to calculate the anomaly, and that will allow you to match, to fix the coefficient of the Wassermann term, whose form otherwise again is dictated by symmetry. So in this way, one can
find the diagram in presence of background gauge fields. That's the key.
Yeah, that's something you can do. Yes, it's possible. It's not necessarily the easiest way to derive the Wassermann terms, but it's possible. Yeah. Okay, so now I'll stop talking about topology, and I'll move to the last part of my talk, which is also the more recent application of the effective theories for GOLDSTONE bosons, and it will now be about different observables, namely scattering amplitudes. And so one more little sort of textbook background. We already know that spontaneous symmetry breaking implies the existence of GOLDSTONE bosons. That's the first thing that we learn usually in field theory. There is another generic consequence of broken symmetries, and that is that GOLDSTONE bosons interact weakly. This is somewhat less robust than the very existence of Goldstone bosons. So there are exceptions to this, but it is sufficiently robust to think of it as a general rule of thumb. And this is actually oftentimes, especially in the scattering amplitude community, referred to as the ADLER zero property. So somewhat more precisely what this means, that if you take any scattering process with some initial state I and final state F, and they don't need to be Goldstone states, you can think of it as nucleons, and you add an extra Goldstone boson, that's the red thing here. Now you can for instance think of this whole process as some pi nucleon scattering on something in QCD. Then the statement is that when you take the momentum of the Goldstone 0 to 0, then the amplitude vanishes in that limit. That means that if you do a series expansion of the amplitude in powers of the momentum of the Goldstone boson, then the constant term is absent, and then you expect naturally that the amplitude starts at the next non-trivial, that is linear order in the powers of momentum. Now there are some exceptions to this, and the exceptions can go in two directions. One direction is that this is not true. As said, so this is the fact that I said in Goldstone bosons interact weakly. The fact that scattering amplitude vanishes in the long wavelength limit means that the interaction is weak, right? Now this is not always true, and this has been known for a very long time. So it's quite surprising that it was only last year, there's a paper in Physics of Letters by Kampf, Novotny, Trenka, and Schiffman, where they actually put down a precise criterion, at least for internal symmetries with compact symmetry group. They put down a precise criterion when the amplitude actually goes to 0 and when it does not. So people have known about this for a very long time, and there was lots of confusion about this. So I would claim that the condition under which the interactions of Goldstone bosons actually are weak at low momenta is now resolved for internal symmetries. There is another possibility of an exception which goes in the opposite direction. That is, it's possible that if when you do the Taylor expansion of your soft amplitude, even the linear term vanishes, and your series expansion starts at some higher order in powers of momentum. So you could start with some power p to the power of sigma, where sigma is larger than 1. And it turns out that there are very, very few theories with this property. There are so few that people started to call them exceptional. And they are not exceptional only because of this, that would be a little bit idiosyncratic. But they have also some other rather interesting properties. And this is what actually I want to talk about in the rest of my talk here. So this brings me to the issue of counting Goldstone bosons, as a matter of fact. So I already mentioned previously that you may have different symmetries which locally corresponds to the same fluctuations of the order parameter. And that means that they will not give rise to independent NAMBU Goldstone bosons. And the simplest example of this is that if you take a crystal lattice, and by this picture, I really meant a 3D lattice. So it's just a 2D cross section, okay? You take some nice cubic lattice, it breaks the 3 continuous translations down to discrete subgroup, resulting into the existence of 3 Goldstone bosons, which we just called phonons, acoustic phonons, 1 longitudinal and 2 transverse. But now we also break continuous rotations, but there are no Goldstone bosons for the broken rotations. And ultimately, the explanation for this is that when you look at the local fluctuations of the order parameter, which is what the Goldstone bosons are, it's really the local symmetries that matter, or the local action of symmetry on the order parameter. So you really need to look at the localized version of your global symmetry to understand the consequences of the symmetry for the Goldstone bosons. And the point being that if you now take translations and rotations, of course, globally they are different. Translation is that shift everything by a constant, rotation is rotation, right? But if you look at them, if you make them local, then it turns out that there is no difference between them. Because translations, what they do, local translations, that they shift you by different amount at different points of space, and rotations do exactly the same. So locally, there is no difference between translations and rotations. And that means that broken translations and rotations correspond to the same fluctuations of the order parameter. And that explains why there are no separate Goldstone bosons for broken rotations in crystals. Now, how does this fit into the picture of scattering amplitudes of Goldstone bosons? Well, you might ask the obvious question. Normally, we are used to broken symmetries being responsible for Goldstone bosons, but now I claim that there are symmetries which do not do any Goldstone bosons. So if they don't, then what is it they do physically? course, symmetries constrain action. You have some nonlinear constraints on the action. You get word identities and things, but you may ask about some more directly observable consequences of such symmetries. And the answer is that they affect the interactions. As it turns out, if you have this kind of hidden symmetries with present, like here, broken rotations, which don't produce their own Goldstone bosons, what they generally do is that they make the interactions softer. That's something that really is has emerged only a few years ago. And I will not show you how this works for rotations and translations, because writing down the effective theory for crystals is surprisingly difficult. I'll show you a different example, which is perhaps more familiar to people working in high energy theory. And this is something called the Dirac-Born-Infeld, the DBI. So here is the action. I have a single real scalar I call theta here, and that's my action. Now I have one obvious symmetry whereby theta shifts by a constant, because the action only depends on its derivative. So that's an obvious global symmetry, and that's spontaneously broken, and that's why theta is a Goldstone boson. And there's an additional symmetry, and I'll show you later where it comes from. There's an additional symmetry where you can make the action invariant if you transform theta and spacetime coordinates simultaneously. This symmetry has a parameter which is a Lorentz vector, beta mu here. So it's actually a set of four symmetries in four spacetime dimensions. It doesn't produce any Goldstone bosons because obviously my action here is only 1 degree of freedom. So there are no additional Goldstone bosons. That's obvious. But if you now take this theory and start expand the square root, so you get a kinetic term and you have interaction terms, you start calculating scattering amplitudes, you find out that the scattering amplitudes vanish with second power of momentum when momentum is small. So that's what I called exceptional. This is the first example of an exceptional field theory. Now, why is this interesting? I'll make a little step aside and tell you a little bit on 2 slides about how we calculate scattering amplitudes of particles. So suppose that still we stick with theories of a single real scalar just to make things as simple as possible. So no spin indices, no flavors, just a single scalar. Now, if you want to calculate scattering amplitudes with a number of particles and for 4-point amplitudes, this is something most of us have probably done. You have to calculate these 4 diagrams. If you now have more particles that participate in the scattering process, the number of diagrams increases and it goes up rather dramatically. And I only show here the number of diagrams up to a total of 9 particles. For 10 particles, I just didn't want to torture my Mathematica with generating all the topologies. So I can just give you an estimate. There will be a total of the order of 10 million Feynman diagrams contributing. Everything for a single real scalar, tree level, no loops. So this makes it clear that if you want to calculate scattering amplitudes for processes with a larger number of particles, which is something that is very relevant for particle colliders, you just run into a wall. You have an exponential explosion of the combinatorics of Feynman diagrams. And that's the reason why many people have been working hard on developing computational techniques for calculating scattering amplitudes without Feynman diagrams. And one very clever alternative that has emerged is based on recursion relations that relate different on-shell scattering amplitudes. It turns out that scattering amplitudes have interesting factorization properties, whereby you can take an amplitude with a high number of particles and factorize it into products of amplitudes with smaller number of particles. So in principle, all you then need to calculate is just say, for instance, some seed amplitude with 4 particles. And from there, you can recursively generate higher point amplitudes. And this operates directly on the full scattering amplitudes. You don't need to consider separately all the Feynman diagrams that would contribute in perturbation theory. But this requires some special behavior of the scattering amplitudes, which is why this was originally devised for a renormalizable theory such as Young-Mills. What's really needed, because it uses the techniques of complex calculus, it needs the scattering amplitudes to vanish sufficiently rapidly at high momentum. And so that's a requirement that obviously is not satisfied for effective theories for Goldstone bosons, which have derivative couplings. And so you have powers of momentum in every interaction vertex, and those powers of momentum just blow into your face when you try to make the momentum large. That's perfectly fine, because the effective theories for Goldstone bosons simply have a built-in cutoff scale, which limits their validity. Yet it turns out, and this is even more recent work by Clifford Chung and collaborators, it turns out that one can modify the recursion relations for scattering amplitude so that one can still apply them to some effective theories of GOLDSTONE bosons, but it requires some additional symmetry. And it turns out that one can devise recursion relations for scattering amplitudes and construct higher point scattering amplitudes from lower point ones exactly for those exceptional effective theories, which have some redundant symmetries that don't do any GOLDSTONE bosons in them. So there's a very interesting link between the modern program of scattering amplitudes and understanding symmetries and their spontaneous breaking. But I will put scattering amplitudes on the side now because I'm not an expert in the calculation of scattering amplitudes, and rather tell you what you can do if you want to look for more exceptional theories that have interesting properties than the one that I showed you until now. Because that would not be nearly enough to establish a whole field of research, right? If there were one action that has some interesting properties. So if you may want to look for additional theories of this kind. And one way is to set a kind of bottom-up approach, and that's what the scattering amplitude people have done. So they basically start constructing the most general scattering amplitude that's consistent with all the locality properties that we expect in field theory. And that satisfies the ADLER zero, so the amplitudes vanish at low momentum. And in this way, you can constrain what kind of theories actually might feature the higher power scaling of the scattering amplitude with momentum. And this is very, very laborious. And people have done this initially for a single flavor of GOLDSTONE boson, then for 2 flavors of GOLDSTONE boson, and that already is very difficult. It turns out that one can also use symmetries. And do the same thing, but from top down. So in the framework of effective field theory, all you need is to know the symmetry breaking pattern. Once you know the symmetry, you know what the GOLDSTONE bosons are, and using the standard techniques, you can construct corresponding Lagrangians. Once you have the Lagrangian, you can calculate scattering amplitudes. So if you are now looking for theories with some extra hidden symmetries, in principle, all you have to do is to understand how you can add to already existing symmetry some extra generators. So it's a question in classification of Lie algebras, basically, essentially. So I'll show you the answer, what it looks like for a single GOLDSTONE boson. Here is the one theory I already showed you previously, what I call the DBI, Dirac-Born-Infeld. Now, all I did was I added an additional parameter V here, otherwise it's the same action I showed you previously. Here is the symmetry transformations. And I added the V there because it turns out that there are 2 versions of the theory, depending on whether the V is positive or negative. The global symmetry differs slightly. And in a way that you can think of this theory is that you can think of it as a theory of a D-brane, where D is our number of space-time dimensions, embedded in a D+1 dimensional space-time, where you have your D-brane that breaks translations in the 1 extra dimension. And then the fluctuation of the D-branes, they are the GOLDSTONE bosons that might field theta here. And now in this picture, first of all, it's obvious where this action comes from, because this is just the induced metric. If you take the metric of your D+1 dimensional space-time and you project it on the brane, this is the induced metric. So that describes the geometry of the brane. Second, this picture also explains the presence of the hidden symmetry, because these additional hidden symmetry transformations just corresponds to Lorentz transformations, which rotate between the physical dimensions and the 1 extra dimension. You have one extra translation, which is this one that's spontaneously broken, and you have a bunch of extra rotations, which are these things. And that's why also the global symmetry is just some SO, some pseudo Euclidean group. So that's a geometric interpretation of the DBI theory. There's another class of theories with a single flavor GOLDSTONE boson, which are called Galilean. They are popular in cosmology, and they look sort of more nasty. So I will not go through the details of the Lagrangians, but I'll just show you what the symmetry is, because it's extremely simple. On top of this symmetry, under which you shift your GOLDSTONE field by a constant, there is an additional symmetry where you shift the GOLDSTONE field by something that's linear in the coordinate. And I believe that this form of the symmetry transformation, which looks like a Galilei transformation of the complex phase of a Schrödinger field. I think that's the reason why people call these theories Galilean. But otherwise, it's a kind of misnomer here, of course, because we are still in a Minkowski spacetime. We have a Lorentz invariant field theory. There is nothing Galilei about this. It's just that formally the form of the symmetry transformation looks kind of like a Galilei transformation. And it turns out that that's it. So among theories with a single Goldstone boson, there are only these two, which are exceptional in the sense that I mentioned previously. But so one can ask the same question in theories which have multiple flavors of Goldstone bosons, because, well, if you look for theories with interesting behavior, two is not enough. And second, if this should be ever relevant for particle colliders, then typically also you have different types of particles, not just one in multiple copies in your scattering process. And so and here is where already the bottom-up approach, where you just try to constructively find all the possible scattering amplitudes, it really becomes very difficult. But from the point of view of symmetry, just classifying possible symmetries and symmetry breaking patterns, there is not so much more difficulty involved. And it turns out that this can be done. I'll not show you details because this is a bit technical, but it's something that I did together with my PhD student, Mark Bochers, a couple of years ago. And quite intriguingly, it turns out that there are whole infinite classes of exceptional theories which have some redundant symmetry hidden in them, but they all share the same geometric interpretation I mentioned in the connection with the DBI theory. So you have, if you take, say, n flavors of Goldstone bosons, you can associate them with n extra dimensions. And in those extra dimensions, you have some spontaneously broken translations, which are responsible for the Goldstone bosons. You have some rotations, which can be of different types. You can have rotations in the extra dimensions. You can have rotations between the physical dimensions and the extra dimensions. And you have also some metric in the extra dimensions. And if you this is just a Lie algebra classification problem. And it turns out that all possible Lie algebras which feature some redundant symmetries have the form of pseudo-Euclidean algebras with some extra dimensions. One can go to some more details. Yes, please.
So is this like saying in a very colloquial way that you're finding many loopholes of the Coleman mandula?
Oh, that's a very good point. That's a very good point. And no, I mean, no, certainly I wouldn't call it a loophole. But the thing is that the Coleman mandula theorem is a theorem about the symmetries of the S matrix. So it's symmetries which are not spontaneously broken. Here I'm putting forward lots of symmetries which do not commute with space-time translation. So they don't commute with Poincare, obviously. And they are consistent with the Coleman mandula theorem because all these symmetries necessarily have to be spontaneously broken. So in that, it's not, there are no loopholes to Coleman mandula theorem, but of course this connection is very interesting. So I mean, you can consider rather general algebras which do not contradict the theorem, yet they lead to very interesting physics. Thanks. That's a very good question. So I'm wrapping up because I'm running out of time. So let me just in passing mention that until now, what I have told you about these exceptional theories was everything Lorentz invariant. And one can start playing the game, what happens if things are not Lorentz invariant. And this may have different motivations. So you may, of course, wonder about possible applications to condensed matter physics, although it's a little bit questionable because scattering amplitudes are somewhat less important in condensed matter physics than they are in high energy physics. You can, of course, think of models for non-relativistic gravity or non-relativistic string theory. And I'm sure that there are many people in the audience who know much more about these topics than I do. So I'd rather not venture in these directions. I just mentioned this as possible motivations. You simply might want to construct field theories which have other kinematic algebras than Lorentz or Poincare. And so actually with the results that we had previously with Mark Bochers, one can just apply them immediately to theories where the kinematic algebra can be Carroll, Galilei, or Bargmann, which is just central extension. This Aristotle, I have heard the name Aristotelian algebra. It just means that you abandon completely boosts. So you only have space-time translations and spatial rotations only. So that's a kind of most trivial non-relativistic space-time symmetry you could think of. These kinematic algebras, by the way, they are also classified. What I'm showing you here is just a small subset of possibilities. And there's a very recently published paper on this, actually a month ago, that where I basically extended the discussion or the classification of possible exceptional theories which have some hidden symmetries in them to this non-relativistic setting. And I'll just show you one example because this is something that I'm currently working on with the student, Martin Mojahed. So this is still ongoing. So this 2021 doesn't refer to date of publication. Okay. So here is one interesting example of a purely non-relativistic theory, which is a theory of a brain that's in some extra-dimensional space-time. So this is like a variation on the DBI theory I mentioned before, except that now you add two extra dimensions. So you have two flavors of Goldstone bosons, and you can think of them as a real and imaginary parts of one single complex scalar. And it turns out the thing is that one can now add a term in Lagrangian which contains one-time derivative, which is like a term with the one-time derivative in the Schrödinger action. So for a non-relativistic scalar, this also turns out to be a Wess-Zumino-Witten term. And there is an extended symmetry still corresponding to all the extra dimensional rotations and translations that you would have. Then you have this term, which is just the determinant of the induced metric as previously. So it's the metric induced on the two-dimensional brain. This is a very, very intriguing model in that you have, you start with some high-dimensional space-time where you have D brain in D plus one-dimensional space-time. You have two broken translations, and so it's like obvious that you have two Goldstone boson degrees of freedom. Yet they are canonically conjugated, and they correspond to a single mode in the spectrum, which is a type B Goldstone boson. This is also interesting because this time the presence of this Wess-Zumino term doesn't arise from non-commuting symmetry generators, at least not classically, because the two modes we have correspond to two translations in two different directions, which classically commute. But it turns out that in presence of this term, the commutator of those two picks a central charge. So this is really like a truly quantum phenomenon, where on the quantum level you have two translations in two different directions that don't commute with each other, and then they conspire to give you this purely non-relativistic type of behavior. So we're now looking at the behavior of scattering amplitudes in this theory, because as far as I know, nobody has ever looked at properties of scattering amplitudes in non-relativistic field theories, whether of this kind or another. But that's really the end. Let me very briefly conclude, not by summarizing everything I have told you, but by briefly mentioning things I have not told you about, because there will be a lot of other stuff to mention. One thing that's my favorite topic would be so-called massive number Goldstone bosons. So these are particles which are Goldstone bosons by all possible means, except that they are non-massless. So this kind of violates the usual paradigm of what a Goldstone boson is. They are particles that have a mass, and that mass is protected by symmetry. It doesn't get radiative corrections. It's exactly calculable. I really have not said so much about broken space-time symmetries. I talked a lot about symmetries which don't commute with Poincaré. As Ian asked, so symmetries which kind of seem to violate the Coleman-Wandler theorem. I haven't really talked about genuine space-time symmetries. Which would be spontaneously broken physical space-time symmetries. There is a lot of formalism that was developed in this direction, and one can then, once you break space-time symmetries, you have a whole bunch of interesting applications, oscillations of topological defects, for instance, surface wave and other things that really find lots of applications in condensed matter physics. And well, one topic that has been rather popular in the last 5 years or something is higher form symmetries, where one can also phrase some of the effective field theory that I presented here for higher form symmetries, and there have been some people in the community that have been applying the new paradigm of higher form symmetries also to low energy effective field theory, such as hydrodynamics, for instance. So I just list some relevant works here, but there will be a lot more to mention. Okay. That's all I wanted to tell you. Thanks a lot for the attention, and I apologize for drawing over the time, but nevertheless, I would be very happy if there were any questions.
Thanks, Thomas, for this very broad and exciting talk, and we learned a lot. Yeah, and then it's time for taking questions now.
I have a simple question. The dilaton, is it also exceptional?
Yes and no. That's a very good question. I skipped it. So when I was talking about these effective exceptional theories with a single flavor of Goldstone boson, if you just classify Lie algebras, actually you would find three options. One would be the DBI, one would be the Galilean, and one would be the broken conformal symmetry where you have the dilaton. and where those redundant hidden symmetries are the special conformal transformations.
Mhm.
So in that sense, it's perfectly right. From the point of view of symmetry, the dilaton would be the third one. However, I didn't include it here because the dilaton does not have this property that its scattering amplitudes vanish in the soft limit, in the long wavelength limit. And the reason for that is because the dilatation generated doesn't commute with space-time translations. So this is one of those exceptions that I mentioned. So how can you have a spontaneously broken symmetry which does not have this property? And one possibility how to violate this property if your symmetry generator doesn't commute with translations.
Okay.
So that's why I didn't include the dilaton here, but otherwise you're absolutely right. It would actually belong to the list also.
Okay, thank you.
Thank you.
Sorry, could I ask a very simple question?
Please.
It was a very nice talk. Thank you. I'm really puzzled by one statement that is in this slide that you're showing now. Maybe I'm missing something. You said that this amplitude should go to 0 if I take the initial and final state to be some nucleon, for example.
In principle, it doesn't matter what the initial final state are, yes.
And the P is the pion with the vanishing momentum?
Yes.
But if you take the historical example of pion exchange between nucleons, it's supposed to give the Yukawa coupling, right? So if it goes to 0 in the zero momentum limit, I mean, I'm not able to reconcile with that fact.
Yes.
What am I
that's
missing?
Right. No, that's a very good point. So the thing is that so in the old historical example, when you write a pion nucleon coupling, it doesn't contain any derivatives, actually. So you might wonder, okay, so this cannot possibly vanish at low momentum. You know, it's just that you just create a pseudoscalar operator, pseudoscalar isospin isovector bilinear out of nucleons and couple it to the pion without any derivatives. But so this doesn't seem to vanish. But then you can start manipulating if you use the Dirac equation for the nucleons. You can rewrite it in a way where the coupling of the pions is derivative coupling. And I believe this goes to what is called the Goldberger-Tremann relation in low energy nuclear physics. But eventually the coupling of the pions will not, the amplitude will not exactly vanish simply because the pions are not exactly massless. They are not exact Goldstone bosons because the chiral symmetry in QCD is only approximate. But so there is a way to make that coupling of pions to nucleons derivative, but nevertheless, the scattering amplitude will not vanish exactly.
Thank you.
Thank you.
Any more questions? What about students in the audience?
I have a question. In string theory, when we write the effective field theory of D brane, in addition to the transverse motion, we get gauge fields. But can you understand that appearance of gauge fields on the branes from your setup in field theory?
I'm not sure.
Okay. I'm
not sure. I know that there were some more recent works actually of the same group here. So there's Cheng and there's Caltech Prague collaboration, Cheng, Kampf, Novotny, Trnka, where they also looked at how to couple these kind of effective theories to vectors, to vector fields, and then look at possible, soft behavior of vector particles. But as far as I know, they were not thinking of those vectors a priori as gauge fields. So they were just thinking of them as some vector fields. And I think one of the motivations for that was trying to understand if by any chance the gauge invariance somehow emerges if you impose some constraints on the behavior of scattering amplitudes. So, you get like, a gauge field as the only possibility. But I haven't quite followed that, so I can't really answer. So from the bottom up perspective, this way where you just start from symmetries and in constructive theory, I don't really see the possibility how the presence of gauge field would be required.
Thank you.
Thank you.
Okay. Any more question?
Hello, sir.
Yes, please.
I have a question. Rather, I need a clarification. In the beginning, you were talking about the type 1 and type 2 Goldstone boson.
Yes.
So can you please elaborate the domain of application? I mean,
Yes.
we have two types of bosons, but what are the, in which case we apply which one? Can you please?
Yes. Yes. So it just depends completely on the on how the symmetry is broken. So okay, normally when we learn about spontaneous symmetry breaking, we learn that the low energy data, so to speak, we need is just to know how the global symmetry is broken down. So we need to know the whole symmetry group and the unbroken subgroup. This is only true in Lorentz invariant systems. In a non-relativistic or non-Lorentz invariant systems, there is an additional ingredient in the of low energy data you need, which is you need to know whether you have some charge density in the ground state. So you need to know the symmetry breaking pattern and expectation values of conserved charges in a system. Once you know those, you can exactly say how many Goldstone bosons of either type you are going to have. Because if you think of your symmetry generators furnishing some Lie algebra with exceptions like the central extension I mentioned towards the end of my talk, this commutator here will be a linear combination of broken charges. And so you will know this if you know the expectation values of all conserved charges in the ground state. So this is this actually relates to the question that Ian asked. So having these kind of Goldstone bosons requires breaking Lorentz symmetry, because if the expectation value of any charge density in the ground state breaks Lorentz symmetry, either spontaneously or it can be broken already explicitly. So you have to look at dense systems. You have to look at matter. But once you do that, there are a number of applications of this. I mentioned ferromagnets. That's one example where you have a type B Goldstone bosons. Also in the so-called A phase of superfluid helium-3, I believe you have another example of this. People notice these weird Goldstone bosons in some models of dense quark matter, models for Bose-Einstein condensation of kaons in high density nuclear matter. People actually, this was kind of known by condensed matter people for a long time, and then this classification of Goldstone bosons was rediscovered by people in the high energy community, in the quark matter community in the early 2000s. And there are other examples. So nowadays, these type B Goldstone bosons have also been seen in ultra cold atomic gases. When all you need to do is you have to take two different types of atoms, throw them into a trap, cool them down, right? So you get Bose-Einstein condensation, and you have to make sure that you have a perfect symmetry between the two flavors of atoms. So you have some kind of SU2 symmetry. And you need non-abelian symmetry that's spontaneously broken, because if your symmetry is abelian, then this commutator just vanishes, and there are no type E Goldstone bosons. So people have also seen this kind of quadratic Goldstone boson in cold atomic gas experiments, where you have, like, it's called spinor condensates. You have multi-flavor atomic mixtures. So there are examples of this kind where this kind of weird NAMBU Goldstone bosons appear. Yeah. Alan, does it answer your question?
Yes, sir, definitely.
Okay.
Thank you, sir.
Thank you.
Okay, Pritam, thanks for the only student to ask a question. So I guess it is time to close. So I will ask a very down-to-earth question about what's the motivation for computing these amplitudes in non-relativistic theories? Is it has some phenomenological applications in condensed matter?
Yes, so that's a very good question. And for me, I must say that it's just a matter of curiosity. So to see, okay, what kind of interesting field theories there might be, but in a slightly different non-relativistic version, this may be relevant for strongly interacting matter, because there are effective theories which are effectively Lorentz violating even in high energy physics. For instance, the so-called heavy quark effective theory, where you have mesons or composite particles which contain some heavy quark flavor. It turns out that they can be described by effectively non-relativistic effective theory, because you have some very heavy particle like the heavy quark, for which you have essentially non-relativistic description. So then you can have scattering processes, including including some mesons that include heavy quark, which are described by some effective theory. That is, well, it's not purely non-relativistic like the thing I showed you here, which is really like Schrödinger-like. That's an extreme case, but it's not Lorentz invariant. So that, of course, that's, I mean, once you drop Lorentz invariance, you have a huge world to explore. And so I'm just interested in this thing right now because this is like an extreme case of a non-relativistic behavior. But there are other interesting options, as well. Martin here that is working on this has actually discovered that are worth looking at. So you can have theories where you don't have this kind of term, where you have like linear dispersion relations, only type A GOLDSTONE bosons, and still once you decouple the temporal and spatial indices, so you drop Lorentz invariance, you can get a more interesting behavior than just Lorentz invariance theories. And people have also looked in those kind of theories in the cosmological context, actually. So there are people in UK, in Cambridge, who think of cosmological applications where you think of having cosmological fluid on top of which you look at behavior of perturbations, and there you can also have naturally non-Lorentz invariant effective field theories. Although again, they would not be of this extreme type. It would rather be of just propagation of some, say, sound waves with a speed that is not the speed of light, and with Lorentz breaking interactions.
Thanks. So in principle, if in EIC you manage to create this dense matter, then if the jets, to understand jets, we will need what you're working on, essentially.
I wouldn't dare to make a strong statement of the sort. So I mean, much of this is like there are aspects of the scattering amplitudes, of course, which are clearly motivated by the collider experiments. So you can actually speed up calculation of scattering amplitudes by orders of magnitude by using the recursion relations rather than by calculating the Fame diagrams directly. But there are also more like curiosity-based motivation. So, for instance, there are many people in the scattering amplitude community who really try to construct the scattering amplitudes directly, not starting from Lagrangian. And it's a kind of revival of this old S-matrix program, where people are trying to construct field theories without the Lagrangian, just by imposing some basic constraints, which should be unitarity, locality, cluster decomposition. And now you just add to it the constraint that the scattering amplitudes vanish in the limit of low momentum. And I see, okay, what kind of scattering amplitudes I can get. So there are lots of people in the US, especially, who work in this direction, whose motivation is simply can we set up a different conceptual foundation for field theory than symmetries and Lagrangians. And they end up basically discussing exactly the same types of theories. So there's DBI and Galileo, which have many other exceptional properties that I haven't mentioned here.
Great. So let's see if there is a closing question, maybe. Okay, so I think it is time to wrap up. It's great to know about your research, and it's purely curiosity driven, but it has so many applications, definitely, and we'll find more. So it was great to learn about it.
So.
And
thank you very much.
Thanks for giving this nice talk and nice colloquium. So we hope to see you in Chennai at some point then.
I'll be very happy, of course, once we are allowed to travel again. Yes, at some point in the future. Yeah.
Okay, so have a very nice rest of the day.
Thank you very much. Yeah. Take care.
And goodbye, everybody, also.
Bye.